Stars give warmth and light to planets and make life possible until they run out of fuel and die themselves, but could these dead stars still enable life to dwell around them? There are hundreds of billions of stars in this galaxy, and most are smaller than our Sun, and even of those that are bigger, virtually all will expand to a red giant one day, then shuck off their outer layers and collapse inward into a burned out husk called a white dwarf. This is the fate of 97% of all stars, including our own, and so it stands to reason that we might want to have a game plan for living around them. Indeed, even though most stars that have ever formed are still alive, we still have around 10 billion white dwarfs in our galaxy already, including over a dozen in our nearby interstellar neighborhood out to about 30 light years. So while every civilization probably needs to have a plan for living around white dwarfs eventually, it probably behooves them, and us, to have a plan even sooner. We will also be exploring some new megastructures and variants that work well around white dwarfs, and brown dwarfs too for that matter, such as strip wards or solar bracelets. So our journey today is going to take us to the heights of mega engineering and the depths of deep time, which means we'll be here for a bit, and a drink and a snack might be a good idea, and don't forget to hit the like and subscribe buttons while you're at it. Now, our goal today is not to rehash the basics of what white dwarfs are or how they come to exist. I think most people do know that, but a lot of times that's about where that knowledge ends. So while this isn't an astronomy course, we will deep dive some of their function, especially some critical bits that I've noticed tend to get left out, even a lot of the deeper discussions of them. Stars burn hydrogen in their core, and this is a dreadfully slow process. The bigger they are, the higher the pressure and temperature they can get, and thus they burn way faster. But this also means that virtually all that fusion is going on in the core, and bigger stars don't really bubble and mix their insides much to move fresh hydrogen in from outer layers and remove helium. Bigger stars can burn helium into carbon, and that too into heavier elements, and those become Type II supernovae when they die. Everybody else slowly gets hotter and goes into a subgiant phase, which can last a very long time, then red giant, and then a planetary nebula that scatters its outer layers and leaves you with a white dwarf that begins very hot and slowly cools. That life cycle depends on the star, and most white dwarfs in existence came from bigger stars than our own Sun, which I'll clarify in a moment, but our Sun, which is 4.5 billion years old, is expected to grow gradually hotter till at about twice its current age it slips into being a subgiant. This is not a fast transition either. The Sun's core will burn up fuel and contract a bit, which will ignite fusion in the layer of hydrogen right around that, and this subgiant phase will last for around 1 billion years. The red giant phase comes on just as slowly and will probably last about 500 million more years. Bigger stars do this all faster, smaller stars slower, though it's not as smooth as a percentage of their lifetime, and the smallest stars won't even have a red giant phase and will live over 1 trillion years. The end comes when the Sun's core finally burns through all that helium, turning it into carbon, and it can't burn anymore, and basically separates into 2 distinct bodies that are about the same mass. The outer shell of the red giant, which is considerably thinner than air, and stretched out possibly as far as Earth, and that contracted inner core of carbon, and the former becomes a planetary nebula, while the latter collapses into a white dwarf somewhere around Earth's size and about half the Sun's mass, which will spend billions of years cooling down. Incidentally, planetary nebulae have nothing to do with planets forming, and the description is from the late 18th century when an early examination of them got described by William Herschel, the guy who discovered Uranus, as looking like a planet, which is to say it looked like a blurry blob through a telescope, like Uranus did, rather than a bright tiny dot the way stars do. This further got cemented when the gentleman who discovered the Ring Nebula, which is a planetary nebula, described it as very dim but perfectly outlined. It is as large as Jupiter and resembles a fading planet. So the name stuck. Ironically, so did asteroid, which means star-like but describes minor planets rather than stars. That said, these nebulae don't really eject at high speed the way supernovae do, so a lot of their material could be collected locally, and probably does get grabbed by various remaining planets, and places like Jupiter and Saturn would largely survive a red giant phase, though their moons probably would not, so they might sweep up a lot of this nebulae. Planetary nebulae are a great source of carbon, nitrogen, and oxygen, which are basically the three biggest things you need for building planets and ecosystems. Those elements plus hydrogen give us methane, ammonia, and water, and those elements plus hydrogen also make up 96% of your body mass, and the same for most organisms. So a star that's turned into a white dwarf isn't necessarily a dead system for all time, even if it's not too likely any planets that were life-bearing before it was a red giant are still around as more than cinders, and any that were habitable while it was a red giant will be much too cold. Smaller stars that live far longer than our Sun might have modest enough red giant phases to not move their habitable zone too far, but again, none of them have died yet for us to observe. A white dwarf is much dimmer than the main sequence star that birthed it, let alone when it was a subgiant or red giant. Ironically, it's now much hotter than before, it's just brightness is a mix of surface temperature and surface area. Normal stars are huge, and thus produce enough light to warm planets tens or even hundreds of millions of miles away. White dwarfs are typically planet-sized, and dimmer as a result. Sirius B, the tiny pup star neighbor of Sirius A, one of the brightest stars in our night sky, actually used to be a bigger dog and brighter than Sirius A. And about 120 million years ago was a massive red giant star that would have been the brightest nighttime object in our sky if it were near us then like it is now. We think it massed 5 times as much as our own star. Now it masses about the same, 1.02 solar masses, with a surface temperature of 25,000 Kelvin, 4 times our Sun's surface temperature. But because it's less than 1% of the Sun's radius, its total luminosity or brightness is just 5.6% of our Sun's, and much more strongly in the ultraviolet region, so it would have a hard time keeping even our own planet Mercury warm, and would be a fairly harsh spectrum for biology and biochemistry to take place under. While we tend to say white dwarfs are roughly Earth-size, they do vary quite a lot in size and mass, and even more in luminosity, a trend that will continue as the universe ages. The smallest white dwarf we've yet found is slightly larger than our own moon, a good deal smaller than Earth, and yet outmasses Earth by a factor of roughly 450,000, which indeed makes it about 36% more massive than our Sun, and fairly close to the limit where white dwarfs turn into Type 1a supernova. Alternatively, the least massive white dwarf yet detected is only about a fifth of our Sun's mass, and closer in size to Saturn. For stellar remnants, the more massive they are, the smaller and more compact they are. This particular tiny white dwarf is believed to have lost mass to a binary partner, in this case another dead star, as white dwarfs win the binary tug-of-war for mass with normal stars, which is what lets them reach that mass limit and explode. White dwarfs are not very bright and thus hard to see, and this one is only 7,000 light-years away, so in our sector of the galaxy as it were. There are probably less massive ones too, however, only by losing mass this way could you realistically have a white dwarf this small, at least while the universe is this young. The more massive a star is, the shorter its lifespan, and most stars are a lot younger than the universe, and as such, most stars that have ever existed are still alive. We would not expect any star less massive than 90% of our own Sun's mass to have burned out its fuel and gone red giant or white dwarf yet, even if they were amongst the very first stars. See our episode Primordial Planets for more discussion of the timelines of these earliest stars and planets. Stars lose a lot of mass when they go red giant, but not enough for any naturally occurring white dwarf to be much under half a solar mass, and most are about 0.5 to 0.7 solar masses and have a radius about 1 to 2% of the Sun's, again making them roughly Earth-sized. The bigger ones tend to be the less massive ones. Most we have found are between 8,000 Kelvin, just a bit hotter than our Sun, to 40,000 Kelvin, about 7 times as hot as our Sun. But the cooler ones are harder to see, and the hotter ones are rarer and spend less time in that range, and often would still be obscured by their planetary nebula during this early period. Now if we know their size and their temperature, we can calculate their luminosity, how bright they are, as they are solid black bodies that radiate light at a rate linear to their surface area, or the fourth power of their temperature. One twice as wide thus has 4 times the surface area, and radiates 4 times the light, while one twice as hot radiates 2 to the 4th or 16 times the light, and cools down 16 times faster too. Using 1% of the Sun's radius and 8,000 Kelvin as our lower end of normal, and 2% of that radius, and 40,000 Kelvin is the higher end. Most white dwarfs are between 0.03% as bright as our Sun to 80% as bright as our Sun, which would put their habitable zones at between 1.7% of Earth's own distance to 89%, or 0.017 astronomical units, or AU, to 0.89 AU. Over many hundreds of millions of years, they will cool appreciably, and that zone will shrink while also growing less harsh as a spectrum. As they cool, the rate they cool at decreases, as does the speed at which their habitable zone shrinks. White dwarfs don't produce new energy the way main sequence stars do, by fusion, which is why we call them dead stars. They are just big glowing embers slowly cooling off. Ironically, until a little over a century ago, we assumed that was how all stars worked, heated by gravitational collapse and slowly cooling. New ones can be as hot as 250,000 Kelvin, 40 times hotter than our Sun, or even the coolest of white dwarfs, the very oldest, nearly as old as the universe, would be just a little colder than our Sun. They would also be much bigger white dwarfs, since in order to be perhaps 12 billion years old, they would have had to begun with a star that was just under the threshold to go supernova, so they would have had more heat to get rid of too. As the universe ages, we'll get white dwarfs that no longer radiate any visible light. As is, most will give off the majority of their heat energy in the ultraviolet range. This is pretty critical to potentially colonizing them, as once they're under 10,000 Kelvin, they are giving off a survivable spectrum of light and might be emitting about a thousandth the light our Sun does, which is itself about 2 billion times what Earth needs. However, there's also gravity to think of, because a star only a thousandth as bright as ours is requires you to be about 33 times closer to it than Earth is to live, 0.033 AU, and that's very nearly the distance at which a shell around our Sun would have Earth-like gravity on it, at about 0.023 AU. A shell built around this hypothetical white dwarf at that distance would have 83% of Earth normal gravity. This is going to be very rough on a planet in that range, since it's going to be close to its Roche limit. Anything but a perfectly circular orbit is going to be harsh on tides. Indeed, planets further out, getting less light, might be able to stay warm by supplemental tidal heating. And obviously there are no natural planets this close to a white dwarf, unless it stole some off some other star that passed dangerously close. Very dangerously too. If a white dwarf gets above 1.4 solar masses, it detonates as a Type 1a supernova, either leaving nothing at all behind, or possibly a zombie star in some cases. So putting a shell around one is a good way to avoid this, and it also allows you to redshift your light to something nicer. As we've been building up to, we shouldn't expect natural life or colonizable planets to be common around these stellar remnants, and they are great for colonizing, but you have to be willing to do some building first, the stellar real estate equivalent of an old fixer-upper. As mentioned, there is likely to be a lot of carbon, nitrogen, and oxygen lying around that outer system. Planetary nebulae usually are only moving 20 to 30 kilometers per second, which makes them decently capturable by other existing objects in that outer system, and there should still be plenty of rocks left over in the outer system that didn't get evaporated by the red giant phase. You should have plenty of material to make some sort of megastructures, but our ideal case here would be tungsten, since it has a high melting temperature, and a thin shell of that around a star, or a thin swarm of satellites if a rigid shell is too tricky, could be placed at a distance just far enough to not melt, and will re-radiate light at a lower temperature, absorbing the harsh UV light and letting something redder out. A non-total shell, one with some holes, or a cloud swarm that wasn't opaque, could allow a very nice overall spectrum of filtered and unfiltered light out to those around it. This is not the mass-intensive effort you might be thinking, see our Statites and Lagites episode for details, but it is unlikely you would even need a millimeter-thick shell around that white dwarf, and at a much reduced surface size to the typical Dyson, so even a modest asteroid worth should do it. Of course, you could probably build a thicker shell with more mass, and at a cooler distance, and just live on it, but that's probably more of a black dwarf phase, for once that white dwarf has cooled below the visible threshold. At this point, you could build artificial planets of whatever type you desire, same as you would around any normal star, but more mobile ones like rotating habitats probably make more sense, since over time you will need to slowly contract that sphere to keep it in the same spectrum of light, while its habitable zone around it also contracts, and those habitats need to move. This is a process of billions of years, incidentally, White dwarf lifetimes are generally longer than the stars that birthed them pre-red giant, though this is because most current white dwarfs came from more massive stars. Bigger cools faster, but again for white dwarfs, bigger means less massive and containing less total heat energy to radiate, so these bigger but less massive white dwarfs cool fastest, and everything cools faster when hotter too. So most white dwarfs will spend a lot more time in the 3 to 10,000 Kelvin range of decent sunlight than similarly sized temperatures when hotter. Given that bigger stars live much less long than their smaller kindred, it seems fair somehow that their stellar remnants should live longer to make up for that. So you could have a cloud of megastructures around one of these for billions of years, indeed tens of billions in some cases, especially if you're willing to just collect infrared heat off them to generate power later on. You could eventually migrate to that shell yourself too when it cools enough, though gravity gets rough once you get too close, and this might be something only post-biological life could really contemplate. For white dwarf megastructures, strip worlds and planetary bracelets work well in this context too. These are large orbital rings placed around a planet, usually a gas giant or brown dwarf, at a distance where its gravity has dropped to Earth normal. On Jupiter, gravity is about 2.5 times higher than Earth, so by building a ring 26,000 miles or 42,000 kilometers above its surface, we would have gravity the same as Earth. And if we built a band 443 miles wide at this height, it would have the same surface area as Earth, and might be much wider. Such strip worlds or planetary bracelets, utilizing the active support technologies discussed in the Megastructural Compendium, may be popular habitats around gas giants closer to their sun. However, they may also be constructed around older white dwarf stars, where air walls and tilted mirrors on the side could allow sunlight to be bounced into bracelets, which might contain thousands of Earth's worth of living area. You have large and canted mirrors hanging out to the side, and which are only reflective to the spectrum you want, with the other light being absorbed to run heat engines to produce power. These do need air walls, as otherwise the atmosphere, or atmo ring, is going to just spill over the side down onto that dead star, and will be rather pyrotechnic when doing it. Since your lighting is coming in through those mirrors, you can tilt them on and off to give day and night, and because of their proximity to the dead star, and it essentially being a slowly draining bucket, it is perfectly practical to reflect unused light back down into the white dwarf, which will simply absorb and re-emit it, unlike in our normal star boosting process where we put mirrors over a star's polar regions to reflect light back down on a cooler star so that its surface warms and we see a stronger and hotter spectrum emerge in its equatorial band where its planets are. We'll call this particular megastructure a white dwarf bracelet, where we built a hab ring at the Earth gravity location. By default, this is not rotating for gravity, nor even orbiting at the proper period since that would negate gravity. It is a ring being pulled equally down on all sides, so it isn't going anywhere. At least so long as you put stabilizers on it, which huge sun mirrors could serve as. Though an inverted orbital ring might have its inner ring stationary and the outer spin. Usually you make an orbital ring by having an inner rotating ring that rotates faster than normal orbital speed, while outside is a non-rotating sheath, but it can be done either way, and the reverse version makes a nice launch system. In this case, a spinning outer ring would be on an order of about a day for most objects orbiting something of about our sun's mass at the distance that would equal 1 gravity, so you might have one big fake sun mirror that was its own half-ring statite or lagite that floated above the orbiting ring on a 24-hour relative period and had noon and twilight regions. I should also note that you could spin a ring that needed to be closer to a white dwarf for warmth than allowed comfortable gravity, and that centrifugal force would lower the surface gravity to something more livable. You have a lot of options for megastructures around these bodies and a lot of time too, while things are slowly changing, so you might see several different arrangements and phases of build-up around a white dwarf. You also might make that white dwarf bracelet as big as you can and cover the rest of the star and mirrors facing down to help keep light in for conservation. Indeed, the underside of that habitation bracelet probably is reflective too, whatever parts aren't used for power generation anyway. This could be what we do to our own sun a long time from now, and if it lost half its mass, that bracelet would need to be at 0.016 AU to provide sufficient Earth-like gravity, which means it is 1.5 million miles or 2.4 million kilometers in radius, and 9.5 million miles, or 15 million kilometers in circumference. So if that band is just 21 miles or 34 kilometers in radius, it would have the same surface area as Earth. Given that a slowly cooling stellar remnant is very popular in the dying Earth genre of fiction, back before we really got the life cycles of stars down, white dwarf bracelets fit this trope much better, but not for size, as one just as wide as Earth is would have nearly 400 Earths worth of living area and would still look like a thin wire rather than a bracelet or band. For that band effect, it would be anywhere in the 1,000 to 20,000 Earth size scale. As to how much you could light, this just depends on temperature. If you're building this when it was down to maybe 10,000 Kelvin surface temperature, with a reflective underside still to keep you from burning up, you'd still be able to light nearly a million Earths worth, while reflecting harsher spectra back down to be absorbed and emitted later, preserving your energy. You could slowly walk your air walls in like glaciers marching from the edges of the world at an ever slower pace, to contract your rings with as the white dwarf cooled, so you could keep an ever-decreasing region warm. See our Dying Stars episode in the Civilizations at the End of Time series for more discussion around living on these things once they dip below the visible range, many billions of years later, and for discussion of how to keep stars from going red giant or white dwarf in the first place. But as we saw today, for supposedly dead stars, they offer some very nice colonization options. As we've often noted about so-called short-lived stars, when we're talking millions of years, that's still orders of magnitude longer than any civilization we've ever built. Indeed, if longevity is any measure of accomplishment, even a couple centuries is a good duration, and I would say anything that lasts an order of magnitude longer than it took you to build and populate it is more than worth doing. But given that these white dwarfs live billions of years, and glow warmly enough to light a million worlds while they do it, and some even more brightly early on, I think we can say they're worth having. Of course, the question is what to do with them when they cool down one day below where you can get energy out of them, and one option is always to go ahead and drop some more matter down on them, since they explode when that happens and free that matter up. You might have reserves of hydrogen or helium lying around in a system. Indeed, you might be using these as shell worlds, Edo worlds, or bubble planets to store fusion fuel while enjoying their gravity while living on their surface and slowly trickling matter down to that white dwarf. This will fuse basically instantly, and when it happens in large quantities can cause a classic nova, rather than the supernova that occurs when it gets to 1.4 solar masses. So you might bundle up all your loose hydrogen and helium into such storage planets orbiting the white dwarf's equator, build reflective statites over its poles for reflecting back down and classic power generation, and slowly feed matter from those planets into the white dwarf, so that this new fuel and those reflective mirrors both add to the lifespan of that white dwarf or mini-nova, and massively extend its second life. You just make sure you've got as much as 1.4 solar masses minus what's in the white dwarf in storage. You could make a lot of shell worlds and bubble plants out of that much material, and when you have finally burned through all of that, after hundreds of billions of years at least, you either have a big party and drop the final mass in to set off a supernova for a rather explosive farewell, or pack everyone up, blow it up, and its supernova remnants will help provide the heavy materials for future civilizations. It just depends on if you're doing this to a white dwarf we colonize in a few centuries, or in a few trillion years when new stars aren't as common as they used to be to migrate to. Either way, not a bad run for a star we normally write off as dead and useless. I occasionally get asked what I do for fun and hobbies, and I try to keep a number of different ones going for variety, but board games and tabletop RPGs are a big favorite. My gaming group and I just wrapped up an adventure last night using Pathfinder 2.0, and we've used a lot of systems over the years. I've been with the same gaming group for 15 years now, indeed longer if you count that myself and one of the members, my best friend Bill, used to play together in the army 20 years back, when I first introduced him to D&D. He and I are both very big into deep world building and long campaigns, and it definitely results in more engaged players who just enjoy the game more. That's where a Word Anvil can be an amazing tool for organizing your campaigns or stories, and also for helping craft content and share it. World Anvil, the award-winning world-building toolset, is an amazing suite of software for gaming and world-building that lets you use all the awesome modern computerized options while still enjoying the versatility of pencil and paper gaming, or even writing fantasy and sci-fi novels. Create customized articles and entries, interactive maps, wiki-style presentations, character chronicles, event timelines, genealogies of characters, and many other awesome features to help you craft your world. World Anvil is also amazing for helping you run your game, with a digital GM screen and a campaign manager with support for over 45 tabletop RPG systems, including a robust library of character sheets and stat blocks. Plus, they have wonderful tutorial videos exploring features to make it easy for you and your players to use, and giving great world building and story crafting ideas to help you on your hero's journey. World Anvil has all the tools you need. To try it out, just click the link in the episode's description and start forging new worlds today. This episode airs on April 25th, 2024, which is the 4th anniversary of my marriage to my wonderful wife, Sarah. We'll be heading out shortly after this episode airs for our first vacation alone since we adopted our 3 kids last year, so apologies in advance for delayed replies to comments on the episode. These last 4 years have flown by, as time tends to do when you're having fun, and I could not have hoped for a better companion to travel life with. Speaking of companions, this weekend we'll have a companion episode for today's Colonizing White Dwarfs, with a look at colonizing binary stars and considering their habitability both classically and in terms of para-terraforming options. After that, we'll start May up with a look at the Banks Orbital, also known as God's Bracelet, a megastructural space habitat hundreds of times larger than Earth that advanced civilizations might build as an alternative to terraforming planets. The week after that, on Thursday, May 9th, we'll look at the interdiction hypothesis of the Fermi paradox, which asks if civilizations out in the galaxy might leave large buffer zones between their empires, and ask if Earth itself might be inside one such empty buffer zone. Then we'll continue the alien theme with a look at the reverse case of interdiction, where civilizations sprawl near each other and set up alien embassies. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon, and if you'd like to donate or help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, along with hours of bonus content like Galactic Beacons at go.nebula.tv/isaacarthur. Thanks for watching, and have a great week.